Is it a feedback day? Is it a feedback day? Is it a feedback day? Feedback day. Can you not find it? Can you not find it? Right there. It's right there. Ah, the feedback day.
Welcome to your AP Stats review from the Desmos quiz that was posted, looks like on the 8th of May, so today's date is the 12th. Thanks for being patient. Thanks for answering some of these questions. Hey, if you're answering all the questions, great, but I've noticed some folks aren't answering all the questions. So here's what it looks like from my end. Be sure to answer every single one of the questions. Keep that in mind as we look forward to the assessment coming up next Friday. So, this is probably going to be kind of a longer video. Let's go ahead and just get straight to it. First question, where are you at today? This is where we're at overall. So if I were to describe this scatter plot, well, it does have, so remember when you describe a scatter plot, strength, linearity, and direction. Don't forget your LSD. Not very linear, pretty weak negative correlation. But it looks like most of us are positive. About 3 of us are positive and a little bit energetic. Most of us are positive and tired. There's a few folks that are negative and tired, but I don't see anybody in the bottom left corner, so that's really, really good. So first question. Starting in the 1970s, medical technology allowed babies with very low birth weight, VLBW, less than 1,500 grams, or about 3.3 pounds, to survive without major handicaps. It was noticed that these children nonetheless had difficulties in school and as adults. A study has followed 242 randomly selected VLBW babies to age 20, along with a control group of 233 randomly selected babies from the same population who had a normal birth weight. I think 0.49 is a typo when I found this question. A, is this an experiment or an observational study, and why? So this is an observational study. The reason why this is an observational study is no treatments were imposed on the individuals. An experiment needs to impose some sort of treatment, needs to change something. Really, this one just looked at folks with very low birth weight and folks with not very low birth weight, and just kind of followed them throughout their life. Part B. At age 20, 179 of the VLBW group and 193 of the control group had graduated from high school. Is the graduation rate among the VLBW group significantly lower than for the normal birth weight controls? Give appropriate statistical evidence to justify your answer. Whenever it says give appropriate statistical evidence, we are doing some sort of test. This is part B. So I'm going to label the two proportions here in a second. So part B, give appropriate statistical evidence. So we're going to be doing a full-fledged test. When you need appropriate statistical evidence, you need to find a p-value, you got to find some sort of test statistic. Okay, so I'm going to list out a few things. We're going to do the 4-step process here. So we're going to do our state. We're going to state our null and alternative hypotheses. Okay. So I'm going to say that P1 is equal to P2, and then alternatively, I'm going to say that P1 is less than P2. So this is still all okie dokie, but it could be incorrect if we don't label these correctly. So make sure that you state your hypotheses and then define your parameters. So I'm going to define P1 as the true proportion of VLBW babies who graduate from high school by age 20. And P2 is going to be the true proportion of non-VLBW babies who graduate from high school by age 20. Okay, so P1 is the very low birth weight babies and P2 is the non-very low birth weight babies. So we have our state with our hypotheses and clearly labeled parameters. Okay. Just for reference, I'm going to put the statistics here. So remember, statistics come from samples. So it looks like the very low birth weight. So the very low birth weight, 242, and out of those, 179, and then for the non-very low birth weight babies, we had 233 of them, and it looks like 193 graduated high school. So for reference, I'm just going to keep my statistics around. It doesn't really matter where you put these, so I'm just going to put it now so I can reference these whenever I need to. And so this one is going to be 0.7397, and this one is 0.8283. Okay, so this is going to be a little bit helpful for me. So now I know that obviously here that P1, right, our statistic, the proportion of very low birth weight babies who eventually graduate high school is lower than the proportion of non-very low birth weight babies who graduated high school. So we do have evidence to support the alternative. We need to check to see if this difference is statistically significant. So let's go ahead and start our plan. So random. Yeah, each sample was a random sample. 10%. So I'm going to say this. So 10%, I'm going to check the sample size of 1. So I defined 1 as the very low birth weight. The sample size of 1 was 242, and the sample size of non-very low birth weight babies is 233. And so I can safely assume that 242 is less than 10% of all babies of very low birth weight, and 233 is less than 10% of all babies that are non-very low birth weight. And so now let's do the large counts. So the large counts here, well, 179 is the number of successes in the very low birth weight baby sample, which means that the opposite of that, the complement is 36. So 179 did graduate high school, which means that 63 did not. And then in the non-very low birth weight sample, we had 193 graduate high school and 40 did not. And all of these, all counts are at least 10. So the successes and failures in our sample are all at least 10. So the large counts is also met. So let's go ahead and get to our plan. So I'm going to state the test here. We are going to be doing a 2-sample z-test for P1 minus P2. Okay, so we're doing a 2-sample z-test for a difference in proportions. So I'm going to set up our z-score. So what we need to do is find a test statistic. So I have my, you need a test statistic, and then we're eventually going to get a p-value. So our test statistic is some sort of, you do not have to write this part, it's some sort of statistic minus the parameter over the standard deviation of the statistic. And so in this case here, our statistic is the difference in those proportions from the beginning. So the statistic that we're going to use is not this one or this one, but the difference between them. So I'm going to take 0.7397 minus 0.8283. And I'm just going to actually leave that exactly like I said it. So 0.7397 minus 0.8283. So that is my statistic. My parameter, what I'm assuming to be true, remember that we assume that the null is true until we have evidence to suggest otherwise. So right now I'm assuming that these proportions are exactly the same, meaning that it didn't matter if the babies were in low birth weight or non-very low birth weight. So the difference I'm assuming is 0. And then we get to this, the standard deviation of the statistic. And there's something that we need to consider. So we're going to be using this formula here. I crossed this one out in our class. You can technically use it for this scenario because P1 we are assuming does equal P2. But I always like to kind of keep it in the same format so I don't have to forget. We are going to be doing something that only happens when we do a difference in sample proportions test. Not a confidence interval, but a test. So the very first thing we did is we assumed that the proportions were the same. Essentially what we were saying is that it doesn't matter whether the baby had very low birth weight or non-very low birth weight. That's pretty much what we were saying. It doesn't matter the group that the baby was in. Okay? Something special happens when we assume that. When we assume that the treatment does nothing. What we're saying that 179 of the babies in the very low birth weight graduated high school, and 193 graduated in the non-very low birth weight, which means overall 372 babies graduated high school by age 20. Okay? So 372 out of a total of the number of babies in this study. So there was 242 in the very low birth weight sample and 233 in the non-very low birth weight. So total, we had 372 babies out of 475 that graduated high school. When we do a significance test for a difference in proportions, we are going to be using this proportion in our standard deviation calculation. This is called our P hat CR combined proportion. Pretty much what we're saying is that this the group didn't do anything, and we are going to assume that this was going to happen regardless of the weight of the baby. That's 372 out of 475 were going to graduate in general. The reason we're allowed to do that is because in the very beginning of this test, that is exactly what we assumed. We assumed that the treatment did nothing and that these two proportions are equivalent. So only for a test and a difference in proportions, we use this combined proportion. And so the helpful part there is we're going to be using this formula here. P1 and P2 are just going to be the same exact proportion of 0.7832. You would use different numbers if we were doing a confidence interval and that was it. So I'm going to do the standard deviation calculation here. It's important that you have the sample size to keep everything in a proportion. All right, and so this is going to be our z-score. How do we know it's a z-score? Easy peasy. We're doing proportions, we are going to be using z-scores. I'll do the second step here. This difference is negative 0.086, and then I found this in my calculator to be 0.03782, and we get a z-score of negative 2.34. So something else to think about is that we do need to get a p-value. So if I look up negative 2.34 in my z-table, negative 2.34, those are all positive. 2.3 and then 4. So 0.00, 2.34, 0.0096. So I get a p-value of 0.0096, meaning that if, so you might see a question about interpreting a p-value. It is assuming that there is actually no difference in the proportion of babies that would graduate high school that have very low birth weight versus non. So assuming that there is no difference in those proportions, we would expect to see this result or this difference here of about -8%, about 8% difference, we'd expect to see a difference of that if there's a truly no difference in the proportions. We'd expect to see this difference this likely. This is the probability of seeing this observation under the assumption that the null is true. About, less than a percent chance. So we have our correct formula. We do indicate p hat c. Now, I don't think you need to kind of put it off to the side. If it's shown in your formula, it will be implied that you did use the correct p hat c. And then we have our test statistic with the corresponding p-value. And so now we can make our conclusion. So, since our p-value of 0.0096 is less than alpha equals, it wasn't stated, so it's 5%, 0.05. So since our p-value is low, we reject the HO. We rejected the null. We rejected the null. The null is not the thing that we should assume, so we were convinced of the evidence. We were convinced of the evidence because we have rejected the null. We have convincing evidence that the true proportion of very low birth weight babies who graduate from high school by age 20 is less than the true proportion of non-very low birth weight babies, non-very low birth weight babies who graduate high school by age 20. So we had a low p-value, we rejected the null, we are convinced of the alternative. State, plan, do, and conclude. So be sure to follow the 4-step process. That was question 1, part B. So this wasn't an experiment. However, we can still do a study of significance. We just cannot now. If it's not an experiment, we can't imply one thing causes the other, but we certainly can look for statistical significance still. That's not going to change. All right, next question. Question 2. Shortly before the 2012 presidential election, a survey was taken by the school newspaper at a very large state university. Randomly selected students were asked, whom do you plan to vote for in the upcoming presidential election? Here's a two-way table of the responses by political persuasion for 1,850 students. Multiple choice question here is still really good practice. So we'll just go straight down the line here. The percent of Republicans among the respondents is 41%. Okay, so that means that we're looking at, is that true? So are we looking at this? So here's all the Republicans. There's 712 of them out of 1,850. If I go to my calculator here, 712 out of 1,850 is actually more around 38%. So this is not true. Let's try the next one. So A is not true. The marginal distribution of the variable choice of candidate is given by these percentages here. Okay, so that means that marginal distribution, remember that marginal, if we're talking about the margin in English class, we're talking about the space on the sides. So if we're looking at the candidate of choice, this is the marginal distribution right here. This is in the margin of the two-way table, so it's the totals. So do these numbers follow these percentages? In other words, is 1,029 out of 1,850 close to 55.6%? Turns out it is. All of these marginal distributions, these percentages, so 695 out of this total, 21 out of the total, and 105 out of the total match these percentages. So since that's true, and you can double check those percentages. Since this is the one that's true, I'm going to say that one. I'm not going to waste my time doing the other ones. If you are between the ages of 12 and 18 years old, you need 9 hours of sleep to be fully functional. A simple random sample of 28 students was chosen from a large high school, and these students were asked how much sleep they got on the previous night. The mean of the responses was 7.9 hours, and the standard deviation was 2.1. We are interested in whether students at this high school are getting too little sleep, which of the following represents the appropriate null and alternative hypotheses. Cool. Awesome. So the first one that you should notice is that this one cannot be the right answer because it has an inequality in the null. So it's always an equal to. Then another one that stands out is the mean. So your sample data was 7.9. There was a claim that it should be 9. So as statisticians, we assume that that's true unless the evidence is statistically significant. So we assume that 9 is true, but we actually have evidence against that, and the evidence against it is 7.9. But all we're going to say is this, that the null is that the true mean is 9. We're going to assume that this study is telling the truth. We aren't going to assume that we got the exact number, right? So 7.9 is assuming that our statistic was correct. So A is not true, oh boy. And B is not true because they're saying that our statistic is the number that we're assuming is true. We aren't assuming the statistic is true. We are assuming the null is true. So now it's down to here, but we are curious of too little sleep. So is it less than 9? So it's not equal to 9. Are they getting too little sleep? So the answer here is D. We're going to do this one on the paper. Let's do this one on paper. All right, we're back to paper here. This is question 3. This is multiple choice question 3. I like this one. Kind of just uses the formula, see if we're confident with the formula sheet. A random sample of 200 New York State voters included 88 Republicans, while a random sample of 300 California voters produced 141 Republicans. Which of the following represents the 95% confidence interval that should be used to estimate the true difference in the proportion of Republicans in New York State and California? Okay, cool. So I'm going to calculate these then for a second. So I'm going to say proportion 1 is the New York one. So that's 88 out of 200. And proportion 2 is the Californian, 141 out of 300. So this is New York, California. So I'm going to calculate these. This is the one that's 0.44. So the New York is 0.44. This is 0.47. Okay, so I'm looking at the multiple choice here. It looks like all of the differences are equivalent. And then it looks like all of the critical values are the same as well. So remember that some sort of stat plus or minus a critical value times the standard deviation of the statistic. Okay. So the difference is the difference between these two. Plus or minus the critical value, easy peasy. So it's a 95% confidence interval. So that is a 1.96. And then it comes down to this. Okay. All right. So in this one, we are not doing a significance test. We aren't assuming anything about these proportions. We aren't assuming that the proportions are the same. We have two totally different proportions. We aren't doing a significance test for the difference. We're just trying to see where is the most likely difference located. What margin of error do we have here for this difference of 3%? So since we aren't assuming that the proportions are, the true parameters are the same, then we are not going to be using a pooled proportion. So the correct answer is going to be the one that utilizes the difference in sample proportions formula right here. It's going to be using this one here. So it's going to use the information from the first proportion and then the second proportion. And we're going to be using the same decimals or the same percentages because we are not assuming the proportions are the same. We only do that in a significance test when we set up our null and alternative. So we'll have 0.44 times its complement of 0.56 over its sample size plus separate addition, 0.47 times its complement, 0.53, oh boy, over its sample size. So the correct answer here is C. Yes, the correct answer here is C. Okay, so question 4. A researcher wants to determine whether or not a 5-week crash diet is effective over a long period of time. A random sample of 15 dieters is selected. Each person's weight is recorded before starting the diet and 1 year after it is concluded. Based on the data shown at the right, well, I guess on the left, weight in pounds, can we conclude that the diet has a long-term effect, that is, dieters manage to not regain the weight they lose? Include appropriate statistical evidence to justify your answer. Yep. So in this case here, notice that we are comparing the weights of each particular person. That kind of makes sense, right? I'm not going to compare the weight loss of somebody that's much larger than somebody else. I'm going to compare it to themselves. Okay, so it's kind of like the coffee drinking example, right? If I went a day without coffee, that would be probably a lot of a different experience for somebody that doesn't drink as much coffee that I do. So it'd be important to compare each person to themselves and then look at the differences there. So what we're going to be doing, it says use appropriate statistical evidence, right? Make sure you interpret that as do a full-fledged significance test. So we are going to do our state. Our null is that we do not have 2 samples right now. We have 1 sample of 15 dieters, and what we're going to be doing is taking the mean of all of these differences. So we're going to calculate all the differences and see if the mean is 0 or not. Okay, so we are going to do a 1 sample test for a mean difference, not a difference in means. So you might see, something like this, mu1 minus mu2 equals 0 later. That would imply that we have 2 separate samples or 2 separate populations. We don't have that here. Each person has their own weight. So it's 1 sample of 15 dieters. If it was like, 15 dieters did this particular weight loss program and these people did the exact same thing that they have been doing, then we compared those average weight losses, then it'd be a 2 sample test for a difference in means. But this is a 1 sample test for a difference in means because everyone was paired with each other. This is a paired t-test for a mean difference. So our null is that the mean difference is 0. Alternatively, the mean difference, I'm going to say, is less than 0. And that's okay for right now. It just determines how I define mu d. I'm going to say that mu d is the true mean change in weight loss. And I'm going to state after minus before. Make sure you do that as well. In pounds, this is the big word here coming up, for people like these. For people like these who follow a crash diet. So there's our state. Let's go ahead and start our plan. So I'm going to state it. We have a paired t-test for mu d. It's a paired t-test, or you could say a paired t-test for a mean difference. So random. It's a random sample. 10%. 15 is less than 10% of all dieters. Yeah, and it was pretty vague in its description of the dieters, so I'm just going to keep assuming that benefits me continuing the test. Large counts. Since n is less than 30, we're going to check the sample data. So remember that with means, we do not know the true standard deviation, so we have to use a t-score. Now, if n is less than 30, so I mean, if our sample of 15, let's say that our sample is 45, we wouldn't have to check the sample data, and we could go along and use t-scores. But n is less than 30, so we have to check the sample data for strong skewness or outliers. So I'm going to show you that here. And I'm going to have you folks, there was a question about showing sample data in your free response question. If it comes up, like if you actually have to use raw data. If there's raw data, make sure that you show like a quick box and whisker of the raw data just to confirm. So we'll go to stat edit. What you're going to do is I'm going to put the before weights into L1 and then the after weights into L2. And then over here for L3, I'm going to click enter. And I'm going to look at the differences. So I'm going to, instead of just doing each of the 15 differences by hand, I'll have the calculator do it. And my statistic, I wanted the after minus before. My after is L2. So I'm going to say that L3 is L2, which can be found right above 2, minus L1, which can be found right above 1. If I do that, it gives me the differences. So this is the data that I need to look at. I really don't care about this or this. I care about the differences in the data. So when I'm going to now go to stat plot, and I'm going to look at a box and whisker of L3, not of L1 or L2, of the differences. And if I graph it, it kind of looks a little bit wonky there. I'm going to click zoom 9, a little bit better. So this clearly, no obvious skewness or outliers, pretty symmetric, so I'm good to go. But I would like to get a few, like the 5-number summary would be kind of nice. So I'm going to go to stat. I'm going to go to calculate one variable statistics on L3. So I'm going to keep this as L3, and I'm going to go down to the 5-number summary. So the minimum, maximum, Q1, median, so on and so forth. And I'm going to create the box and whisker from the min, the max, Q1, Q3, and the median. Cool. So now I have this kind of to reference, and there's no strong skewness or outliers. So we're good to go for the large counts. Just a reminder that all of the conditions and procedures can be found in your textbook on the back flap. So there's a lot of stuff. You aren't going to have to do any of these last 3 types of tests, so that's kind of nice. But everything else is there for you, which is great. So it has the number of samples that you have, if it's an interval or a test, and then the conditions that would follow from it. So right now we're doing paired mean test, and so here we go. We're in this category right here. So now we've done the plan. Now it's time to do the do. All right, so we're doing a paired t-test here. Remember that it's always, you don't have to write this part, but we're going to be doing a t-score, and it's some sort of stat minus parameter over the standard error of statistic. This is the standard error because I'm not going to be using the true standard deviation. I'll be using the sample standard deviation. Okay, so my statistic is the mean difference. So the mean difference is negative 3.6. Okay. The parameter is the assumed value, which I said was 0. The standard error of the statistic is the standard deviation of a one sample for mean, but with the true standard deviation replaced with the sample standard deviation, which in my one variable stat has spit out, remember, don't use sigma x, use sx, and that has spit out, you see that all right? There we go, a little better. So I'm going to be using the sample standard deviation of 1.525. 11.525 over the square root of the sample size. So I'm just following this formula right here. Cool. And if I do this, I get negative 1.2098. All right. So now, this is great. So if I go to the t table now, notice my t-score was negative. But since the t distribution is symmetric, the t table only uses the tail distribution, which is really nice. So we can just take the absolute value of that t-score. So we'll use the positive version, and we'll still get the tail probability of what we're looking for. Degrees of freedom. Our sample size was 15, so we're going to look at row 14. We're going to try to find our t-score in this. So our t-score is negative 1.2-ish. So I do that. Row 14, I'm looking for 1.2, and it's caught in between right here, which means that the corresponding p-value is caught in between right here. So our corresponding p-value, So for row 14, my t-score was between these two, which means that my p-value is maybe between these two. So I know my p-value is between 10% and 15%. And I'm going to put degrees of freedom here just in case. Oh, there we go. Cool. So I have my test statistic formula filled out. I have my test statistic value. I have a p-value. And I've stated degrees of freedom. All right. So now we will conclude. So because our p-value is between 10% and 15%, it is greater than alpha of 0.05, so we fail to reject the null, which means we do not have convincing evidence. We did not reject the null. We are not convinced that it's not the null. Okay? So we do not have convincing evidence. We do not have convincing evidence that the true mean difference after minus before in weight for people like these who follow a crash diet is less than 0. We had evidence to suggest that it's less than 0, but the evidence wasn't strong enough. Okay? Remember, our evidence was negative 3.6. So these results could still plausibly happen by chance alone. Woo! Ugh. So I tried to do a few things. I wanted to give you some more tests, some more statistical tests, so we had a difference in proportions. Then we also had a paired t-test, and then one of your multiple choices was a confidence interval as well. I'm going to be posting a Desmos quiz tomorrow, and yeah, I'll be posting a Desmos quiz tomorrow, and then on Thursday we'll have a Zoom I said the time. So it'll be an answer key. We'll do the Zoom at 11. So let's do the Zoom at 11 o'clock. It'd be great if you can make it. We'll go over the answer key and any other questions that you have that I can help out with. Yeah, I think, thanks for watching. If we look at this last question, I'm gonna hit 200 subscribers soon, and you folks want me to, I think it'd be fun to do a wasabi challenge. I don't know what that means, but I'd like to do it. So this person said, wasabi on random foods, pizza, tacos, maybe some sweets like cookies or cinnamon rolls. Rate them from best to worst to have wasabi on them. Do a backflip. And then the cinnamon challenge with the serving spoon, like Closelle. Oh, the cinnamon challenge. Oh boy. Okay, so maybe we'll do a combination of all those. I'll do a backflip. We'll do a cinnamon challenge with some wasabi. And then you probably won't hear from me for a long time after that. All right, take care. Zoom this Thursday, May 14th at 11. Going over the Desmos quiz I'll be posting tomorrow. Thanks for your feedback. Thanks for participating. I know this is tough. Thanks for watching. I appreciate you watching these videos. Take care. Be safe. Wash your hands. See you next time on Math Think.